Okay, so welcome to the week for audio notes. And once again, we divide the slide into about 9 sections. And this will be the part number 1. And I will go with you one by one through the slide material. To make it light, I made it maximum about 10 to 12 pages. I will start with the first one. The topic we're going to cover in the week number 4 is going to be the fundamental of the metal forming, which is usually going to be a process that follow the week 3 topic, which was the casting procedure. So we'll start with the overview of the metal forming, the material behavior in the metal forming, the temperature in the metal forming, the strain rate sensitivity, and the friction and lubrication in the metal forming. Then the second part is going to be the bulk deformation processes in the metal working, and finally we're going to cover the sheet metal working. So let's start with the introduction about the things. The stresses used in the metal forming usually going to be classified to the following types. We have the compressive type, like what we have in the case of the rolling and the extrusion. We're going to add a compression force to reduce the size and shape the part. Second, we have the tensile stress, which is going to stretch the metal. And in that case, we are going to reduce its thickness, and that's what we have in the case of the sheet metal working. We have the tensile and the compressive at the same time, like the bending of the metal, and we have finally the shear stress, which we're going to use in the shear cutting process or the cut of the metal. The material properties in the metal forming are the material with the lower yield strength and higher ductility are going to be easier to be formed. Okay, so when I highlighted that means this can be a possible question in the quiz. So once again, we need a higher ductility and lower yield strength. So not too much strong and should have a good ductility. Otherwise, it's going to be fractured, and that's for the ductility point. And it's going to use too much force. The metal ductility will increase and yield strength will decrease if I'm going to increase its temperature. Okay, now let's tell you why the blacksmith, for example, during the forging, heating up the pot. So what's happening is that the metal temperature increasing, we're going to have better ductility and we're going to reduce the yield strength. Other factors like the strain rate and the friction also affecting the metal forming processes. So the basic types of the metal forming processes are the bulk deformation, and we have the sheet metal working. The bulk deformation is when we start with a block, for example, or a road, whatever the thing is, but we're going to add a force to something that have quite high thickness. So we can do the rolling process, we can do the forging process, we can do the extrusion process, and the wire and the bar drawing. And the sheet metal working on the other side, now the area to the thickness ratio is going to be quite high. Thinner material, we're going to call it the sheet. So we can have the operation like the bending operation, the deep or the cup drawing. We have the shearing processes and other miscellaneous processes related to the sheet metal working. So we start with the bulk deformation processes. The work part with relatively low surface area to volume ratio. That means its volume much higher than well, quite high to make the ratio to be low. It's going to have usually simple geometries like the cylindrical pillars or the rectangular bars, and also to have a significant deformation and massive shape change. So we can have it as a square shape, and we can end up with having a spherical shape, for example. Okay. Let's include the rolling, the forging, the extrusion, and the wire and the bar drawings. On the other side, for the sheet metal working, definitely now the surface area to the volume ratio is going to be higher. So high surface area to volume ratio, like what we have in the metal sheets, the strips, and the coils. The process of the forming will include the bending, the cutting, and other operations. is going to be called the sheet metal working or the press working, because this operation is going to be performed on a presses machine. The parts are going to be called the stamping, and usual tooling is going to be punch and die. Now, for the physics of the material behavior in the metal forming, we are going to have some calculation questions, up to 6 calculation questions, and that will be part of the tutorial. So we start with the behavior of the material in the metal forming. You remember that we have plastic region of the stress strain curve is going to be the primary interest because of the material going to be plastically deformed. So actually, when we shade the part in the metal forming, we would like it to pass the critical point, which is going to be the yield point. We want to move from the elastic region to the plastic region. So in the plastic region, the metal behavior is going to be expressed by the flow curve, that the stress is equal to the K multiplied by the mu up to power n. Now, I think that you remember this equation. We said that this is stress, the K, the mu, epsilon is the strain, the K is strength coefficient, which is going to be different from one material to another, and the n is going to be the strain hardening exponent. This value of the n is going to be reduced as long as we're going to increase the temperature, and this line will be perfectly plastic if we're going to be n value equal to 1. Okay, so flow curve is going to be based on the true stress and true strain. And you can see that the average flow stress in relation to the flow stress YF and the yield stress Y. For the flow stress, for most materials at room temperature, the strength is going to be increases when deformed due to the strain hardening. You remember that we said that if I get to add a strain to any metal, its strength will be increasing. The flow stress is the stress that must be applied to cause the material to deform at a constant strain rate in its plastic region. Okay, so the stress we are going to add at any point here in the plastic region to cause the material to deform at a constant strain rate in the plastic region is called the flow stress. And this can be explained by the same equation. The YF is equal to the K multiplied by the epsilon up to power n, where the YF is the flow stress, and that's it. The yield strength is going to be a function of a strain. Now, how the temperature is going to be useful in the metal forming. Now, you remember this equation. We have the K and we have the N. The YF and the epsilon, the YF is going to be based on these values. So the calculation of that is going to be very easy. As the metal temperature is going to be increasing, both the K and the N value is going to be decreases, and then the flow stress is going to be decreases. So this will make the stress strength less, and thus we can deform the material much easier. So as higher temperature, first we're going to have lower stress. Second, the higher ductility for the material. Accordingly, the lower forces and the power to accomplish the deformation operation is going to be achieved at the elevated temperature. We have 3 temperatures range in the metal forming. We have the cold working, we have the warm working, and we have the hot working. So in the cold working, performed at room temperature or slightly above. And many of the cold forming processes are going to be important in the mass production operation because we don't need to spend more time on the heating of the part and then leave it to cool down. These operations are going to be near net shape, our net shape processes where minimum machining is going to be required, so we can make the part, then use it directly without having any extra machining processes. Why we have that? Because we didn't heat up the part. So no size deformation has been changed, no oxidization happened to the part. Second, for the warm working, performed at temperatures which are going to be above the room temperature, but below the recrystallization temperature. dividing the line between the cold working and the warm working often going to be expressed in the term of the melting point. So the warm working is going to be about 1/3 of the melting temperature. 1/3 of the melting temperature. Now, the last one is going to be the hot working, where it's going to be deformation as temperature is going to be above the recrystallization temperature, or it's about half of the melting point. So the metal will continue to get softened at the temperature that increases above the half of the melting point, and this will be enhancing the advantage of the hot working above this level. So at the hot working, we're going to have the perfect plastic material. The advantage for each one is, for the case of the cold working, we're going to have better accuracy, closer tolerances, because the part not going to be changed in size due to the temperature changes. Better surface finishing, of course. Strain hardening increases the strength and the hardness of the part, and the grain flow during the deformation can cause desirable directional properties in the products, and then no heating of the work are going to be required. But we may need heat treatment. For the warm working, we're going to use less forces and power than the cold working, because the part's getting soft now when we're going to take it to the third of the melting point temperature. More intricate work geometry is going to be possible, because it's going to be much easier to form it, and also need for the annealing may be reduced or eliminated, because the part itself is going to be heated near the recrystallization temperature, then it's going to be cooling down, so this will be annealing a process. In the hot working, the work part shape can be significantly altered, because now it's became much more controllable, because we reduce the stress to the lower value, and also we increase the ductility of the materials. Lower forces and the power are going to be required, because both the K and the N are going to be reduced, and the metal that usually get to be fractures in the cold working can be hot formed, like even the cast iron. The strength properties of the products are going to be generally isotropic, and no strengthening of the part occurs from the work hardening. And this is advantageous in the case when the part is going to be subsequently processed by the cold forming after the operation of the hot working. Still, each operation have disadvantages, like for the cold working, because we don't increase the temperature, so the stress is going to be quite high, and this required higher forces, power for this operation. Also, the starting work surface must be free of the scale and the dirts. The ductility and the strain hardening limits the amount of the forming that can be done. In some cases, the metal must be annealed before further deformation can be accomplished. In other cases, the metal is simply not going to be ductile enough to be cold working, so we cannot use it for the cold working. For the warm working, the workpiece must be heated. For the hot working, we're going to have lower dimensional accuracy, because the part is going to be shrink after the heating up. Higher total energy is going to be required, which is going to be some of the thermal energy needed for the heat of the workpieces and the energy to deform the metal. Also, again, have the work surface oxidation, which is going to cause the scales that some of the material will be simply breaking up, and thus we're going to have the poorer surface finishing. The shorter tool life, because the dies and the rolls and the bulk deformation going to be exposed to a very high temperature, and this will reduce their life and their quality. Now let's talk about the strain rate sensitivity, and we can tell that strain rate is going to be the change in the strain of the materials with respect to the time. So we said that strain will be changed as we deform the part. This can be simply identified as strain rate is going to be equal to the deformation speed, which is the ground velocity that doing the deformation, divided by the instantaneous height of the workpiece, because we compress it, so it's going to reduce its height. Theoretically, a metal in the hot working behaves like a perfectly plastic material, with strain hardening exponent to be equal to 0, or for the n in the equation of the flow stress. The metal should continue to flow at the same flow stress once that stress is going to be reached. The flow stress is going to be a function of the temperature, as we mentioned earlier. So at the hot working temperature, the flow stress also depends on the strain rate, and the strain rate will be increases. The resistance to the deformation will be increases, and this is the effect known as the strain rate sensitivity. So that's the definition for the strain rate sensitivity. So you can see in this figure, on the figure A, the effects of the strain rate on the flow stress at elevated work temperature. And this is the same relationship plotted on the log-log coordination. So again, to have it as a line. So we can find the slope of this line. The C value is going to be the flow stress at the strain rate of 1/second. 1/second, because remember that strain doesn't have unit. Now, the effect of the temperature on the flow stresses, we said that the strain rate sensitivity equation given to us as the flow rate is equal to the C value multiplied by the strain rate up to power m, which is the slope of the line that we show you earlier for the log-log diagram. C is the strength constant, and m is strain rate sensitivity exponent. So you can see at room temperature, we're going to have the higher value for the F. If I'm going to keep increasing the temperature, we're going to have a lower value for the flow stress. The constant C, indicated by the intersection of each of the plot with the vertical dashed line at the strain rate equal to 1, will be simply going to be decreases. And the M, which is the slope of the each plot, will be increases with the increasing temperature. Okay, so what we are going to have is that the C value will be simply going to be decreased, but the N value will be increasing, as you can see here. So this will be controlling the value for the YF. One of them is going to be decreased, the other one is going to be increasing, and we're going to end up at the end by having the different value for the YF at different temperatures. Now, some observations on the strain rate sensitivity. We're going to have a discussion about it here. Increasing temperature will be decreasing the C, but increasing the M. And at the room temperature, the effects of the strain rate is going to be almost negligible. And the flow curve alone is going to be a good representation of the material behavior. As the temperature is going to be increases, the strain rate becomes increasingly important in determining the flow stress, because we said that the C value and the F value are going to be changed. The friction is playing a big role in the metal forming. In most of the forming processes, the friction is going to be undesirable. Because when we change the shape of the part, there will be sliding between the die and the part itself. So the friction is going to make the things worse. The metal flow is going to be reduced in case of the friction. The forces and the power is going to be increasing, and the tool wear will be simply be faster. The friction and the tool wear are going to be more severe if we're going to have hot working. Well, of course, you know that the friction increasing as the temperature is going to be increasing. So we can use lubrication in the metal forming, where the metal working lubricants are going to be applied to the tool work interface in many of the forming operations to reduce the harmful effects of the friction. The benefit for the lubricant is reducing the sticking forces, the power, and the tool wear. Also, again, to achieve better surface finishing and remove the heat from the tooling at the same time. So that will be the end of the part 1 of the audio notes, and we're going to continue with the part 2